the afternoon, and with the talk of Michele Mosca. So I'm really looking forward to this talk about quantum algorithm, and to, as I guess everybody, to understand what we can do in this setting.
Thank you very much. It's a pleasure and honor to be here to lecture about this very important topic, central topic to the for the theme of this workshop. What do we realistically hope to achieve in 90 minutes? One of my colleagues teaches a full semester, 12-week, 36 hours of lectures, course in quantum algorithms, and that's not a comprehensive course. So definitely it's not going to be comprehensive. We're not going to learn to be practitioners. So as Ludwig said, I'm just going to give an overview of some of the tools quantum algorithms give us, some of the new hammers we have to break cryptography. When I was a student, I started off in classical cryptography, conventional cryptography, looking at index calculus methods. So conventional computing, classical computing. And then I learned about quantum algorithms. So because they define what's hard and what's easy in the future when we have quantum computers. And I've always, I was actually in denial for a few months or a couple years, but then I realized it was a question of if and not when. Right? So when we have large-scale quantum computers, quantum algorithms will define what's secure and what isn't. So we have to understand what computational security is in the context of large-scale quantum computers. We're not there yet, but we've come a long, long way since the mid-90s when, after Shor's algorithm, when great attention came onto this field. Our friends at Yale wrote this nice paper outlining the 7 stages to achieving a large-scale fault-tolerant quantum computer. And where we are today is several of the top groups in the world are trying to tackle that middle stage. This, I think, is the most critical milestone. So initially, it was a handful of physicists trying to think of, what could I use to make a qubit? Okay. Now we have some very good ideas of what we can use to make a qubit, and we're very close, I think, to having the design for a fault-tolerant, scalable quantum computer. When that happens, we'll still be doing physics, because the better the physics, the easier it will be to scale. Of course, we'll be trying to improve the physics, but there'll be more and more engineering. It'll be more and more about scaling, about building this scalable design. So we have to watch very closely for this critical milestone to be achieved. Right? And I think there's a very good chance it'll happen in the next 5 years. And then it's a question of how long will it take to scale up to be something that's a true threat to cryptography. Right? So there's a tool chain from abstract quantum algorithms down to the physical hardware. And every link in this chain has some overhead. And the true cost of implementing a quantum algorithm is the sum of all these costs. And there's a lot of work going on now in optimizing all these steps. This lecture will be mostly about this top layer, essentially. It'll be about this top layer where there's the greatest potential for disruptive changes in the difficulty of solving a problem. But of course, whether it takes 1 million qubits or 1 billion qubits has a big impact in practice. So that's very important too. And there's ongoing work in this. There's a nice talk later in the week by Marcus Grassel and co-authors on implementing Grover's algorithm to attack AES, for example. That work needs to be done to tell us how many qubits we'll ultimately need to implement attacks on various systems. So again, this talk will focus on this top layer. So how do quantum algorithms work? Because we all learned very quickly, it's not a magic box. You just throw your problem at it and it gives you an answer. It's not an NP oracle, as far as we know. We don't think it's an NP oracle. It's a very, very specialized hammer, so to speak. It's very hard, in fact, to find problems, to find ways to actually get a speed up using quantum parallelism, or it's proved very hard to date. So very simply, what quantum algorithms try to do, what they can do that conventional computers can't do, not in a straightforward way, is start off in some definite state, but then explore many different states and end up in one of many different states. And there's many different paths that will lead you to any specific outcome. And if you want to know what's the probability of seeing 0, 0, well, that probability is the sum of the quantum amplitudes of all the paths that take you to 0, 0. And then you take that amplitude, the sum of all those amplitudes, square them to get a probability. So these amplitudes, what quantum physics tells us is underlying probabilities are quantum amplitudes, which are essentially a sort of square root of a probability, which have additional information. You take the absolute value squared to get the probability, but there's a richer reality underneath of quantum amplitudes. And to compute the probability of an event, you take, again, the sum of all the paths, absolute value squared. Whereas if this were a classical computation, which you can think of as a quantum one where you're always looking at it, you wouldn't be in a combination of all these paths, of all these states. You'd be in one or the other with respective probability, that amplitude squared. Right? If you compute the probability, it's a sum of the probabilities of all the paths. It looks very similar, except the absolute value is inside the summation and squared versus outside. And sometimes this number is bigger, and sometimes the previous number is bigger. You just get a different distribution. And quantum systems can be easily engineered to look like classical systems to produce the classical statistics, but not vice versa. We don't know how to do vice versa. So we get different interference patterns. So here's a metaphor in a sense. This is a two-slit experiment. Every point on this screen has two different paths that lead to it. And the quantum interference pattern looks very different from the classical interference pattern. Some events are more likely, some are less likely. So the art of quantum algorithmics is to choreograph constructive interference on the outcomes you want and destructive interference on the outcomes you'd rather not see. And that's not easy to do. So let me start giving you some of the historical examples. Right? In the beginning, we had this hammer called the quantum computer, and people made up very artificial problems just to see what the potential of this hammer is. So this is not the first example, but it's one of the first. Imagine you have a function from n bits to 0, 1. It's the inner product of some n-bit string times your input string. And you have a reversible way of computing it. So you take your input, some workspace initializes some string c. You can assume c is 0 if you like. And you XOR the answer bitwise to the second register. Right? Just a reversible way of implementing your function. Determine A. Now classically you'd have to sample n times to determine A. A quantum computer can determine A with one evaluation of that function. Right? Here's the circuit. I'm not going to have time to go over the details of algorithms, but you can see these gates, called Hadamard gates, prepare a superposition of all the possible inputs. Then you compute your function, and then you combine them again, just like in the two-slit experiment, where those two slits combine these two different paths into an array of different paths. And it turns out you deterministically determine the 3 bits you measure, you get here, are the answer. Okay, one query. You can actually generalize this. It doesn't have to be over Z2. You can have any cyclic group of order P. You can go from n bits to m bits, or n tuples, to m tuples. So there's some matrix M. Take an input string, input column vector x, you multiply it, you map it to m times x. Suppose you know how to multiply by m. What the generalization of Bernstein-Vazirani gives you again, in one shot to this circuit for implementing f, you get, instead of multiplying mx, you turn a right multiplication into a left multiplication. Or vice versa. You can go in either way. Who cares? I don't know. But if you can think of a cryptanalytic application of such a thing, that would be very interesting. Or even something not cryptanalytic. Are there natural circumstances where you implicitly know, if the matrix is sitting there in some very, an actual matrix data structure, this is probably not so interesting. But are there ways where you can implicitly multiply from the right or from the left, but you'd like to do the opposite? Because then a quantum algorithm can do the opposite for you with just one shot. I don't know of any killer applications of this, like real interesting ones. So this Hadamard transformation that I mentioned, again, feel free to interrupt. We do have a whiteboard. Happy to answer questions as we go along. Imagine you have n tuples of Z2. Imagine a subgroup of this. We define S perp to be the set of all n tuples that are orthogonal to everything in S. So you can think of this as a vector space. It's the orthogonal space, if you like. So it's a set of vectors, a subspace, subgroup. This is orthogonal group. Okay, we just denote by y plus s a superposition of all elements of that subgroup shifted by y. So this is a coset of your subgroup, right? We use additive notation. Y plus s is a coset. Just take a superposition of everything in that coset. Suppose somebody hands you this. If you apply the Hadamard transform to this, you get a superposition of everything in the orthogonal group, the orthogonal space. There's these funny phases here, but if you measure it, you're always going to see something orthogonal to S. Something such that you're going to measure a t, such that t inner product with S is 0 for everything in S. Okay? So Dan Simon, who was a postdoc at the University of Montreal at the time, in the early 90s, came up with this very artificial problem just so he could show an exponential speed up, a query for a query algorithm for a quantum computer. So you have a function that maps n-bit strings to some set, could be n-bit strings as well, it doesn't matter, such that f at x equals f at y if and only if x and y are in the same coset of some subgroup of Z2 to the n. Again, n tuples of Z2. So in other words, if x minus y is in that subgroup. So you're implicitly defining this subgroup. I don't hand it to you. I give you a function that's implicitly defining it. Now find it for me. Find me generators of this subgroup given just a function, query access to a function, which has a periodicity that depends on that subgroup. Good luck. Okay. Classically, this is exponentially hard. Again, if you only have query access to F, you need exponentially many queries, exponential in n. Dan showed that this circuit will do what? It'll output not elements of S, it'll output a random element of S perp, of things orthogonal to what you want. So I really want to sample S so I can get generators for S. But the quantum algorithm gives us things orthogonal to S, uniformly distributed. So what do? Well, you sample n plus a few times, n plus 3 times or so. Right? You make those rows of a matrix. Each S times each T, each row times S is 0. So you get a matrix times S equals 0. You just do linear algebra to find the generators, to find the solution, all the solutions S. So you solve for S by linear algebra. So here's a question for the audience. So when I was a graduate student, just learning about the field, I thought, well, these quantum computers are going to be really faulty. I'm not going to get a perfect sample. I'll be lucky to get something that's 90% likely to be an S-perp, right? So then what? What do I have? Is that a problem? Can I cope with that? So each t has, say, 90% probability of t times s equals 0, and 10% probability that it's equal to 1. And you're sampling these noisy t's. Who thinks there's an easy fix? If there's a fix, you do fault-tolerant error correction, you make the error rate negligible so it never happens. But suppose you want to skip that step so you can avoid the overhead or some of the overhead of fault tolerance. What do you have here? So who thinks that's easy if you can have noisy samples from S-perp? And who thinks it's hard? Yeah, why is it hard? It's essentially a learning with errors problem, right? So you can solve it, but all the obvious ways to solve it, at the time looked NP hard. So this was not a viable way forward. So you do have to do error correction and make sure these samples are essentially error-free. So who cares, really? To first order in 1993, nobody. Big O of 1 people with a very small constant cared. Paper was rejected from one of the main CS conferences. But here's one of our colleagues wrote, it appears contrived. So the Bernstein-Vazirani problem I told you appears contrived. To this author, this looks a little more natural. Simon's problem looks more natural. I'm not sure how many people would agree that it looks natural, but to this author it did. And it inspired some work in this paper. Any guess what paper this is? Anybody? Yeah. You may have heard of it. Yeah. So this is how research works, right? If a few people are exploring something because they think there's some deep ideas here, we're mining something very profound. I don't know the applications. Right? And in parallel, there's people with hard problems and they're looking for tools to solve them. And every once in a while, you get unexpected collisions. Right? And this is one of them. So a huge breakthrough. Now, there are other applications of Simon's algorithm. Up until recently, I didn't know of any. But some of our colleagues in Japan, for example, showed you can have a quantum distinguisher between 3 round Feistel ciphers and random permutations. So I'll just briefly sketch what this means. So here's a Feistel cipher with 3 permutations. So you have 2n, you have an n-bit register, an n-bit register. You permute things, XOR, and so on. You can just follow the chart. You're permuting and scrambling and XORing. You get 2 n bits out. So let's define W at X. So X is a 2 n-bit string, A concatenated with C. And let's define it with an n-bit output, which is the output of this, just half of the output of this Feistel cipher. Okay, why not? Okay. So the details here don't matter. So you have W, which takes 2 n inputs and outputs an n-bit output. The authors cooked up an n plus 1 bit function. So it takes n plus 1 bits as input. B is 1 bit, A is n bits. It uses this W function, XORs with some fixed strings, alpha and beta. Again, who cares? Well, this is why you should care. They cooked it up in a way such that f at this n plus 1 bit string equals f at some other n plus 1 bit string, if and only if the XOR of these n plus 1 bit strings is either the 0 string or 1 concatenated with the string z, where z is just the first permutation applied to alpha, XOR the first permutation applied to beta. Don't really care what this string is. It's some string. So again, just to repeat. So you start with a Feistel cipher with 3 permutations, 3 rounds, and you get a Simon-like promise. You use the part of the Feistel cipher as a subroutine. You cook up a function that looks like Simon's problem. Right? 2 things are equal if and only if the two inputs are either the same or differ by some fixed string. Now the only if part's important because you can certainly cook up the if part, you just have a constant function. So you need it to be only if, at least approximately. You can start to, it still sort of works if it's mostly true. So if you run Simon's algorithm with this function, you're going to sample vectors orthogonal to some fixed string. So you're not sampling the whole space, you're sampling a very structured subspace. On the other hand, so you want to note, somebody gives you a black box. It's either implementing the Feistel cipher, the 3-round Feistel cipher, or a real random permutation on 2n bits. How can you tell which is which? Well, if you run Simon's algorithm with this f function, you're going to be sampling, you're going to be generating a subspace. And if it's a random permutation, you're going to generate the whole space. So it's a very distinguishable, 2 very distinguishable outcomes. So it's a very nice application of Simon's algorithm. Now it's critical that you can apply the Feistel cipher, so the Feistel permutation or the random permutation in superposition. Okay, so there's no need to panic. Not that this was necessarily a widely used primitive in practice. There's no need to panic because there is an extra assumption for the attack to work that you can query in superposition. And various authors, including some very recent work just a few days ago, it's always fun when you're preparing a talk and there's cutting edge results coming out days before, hours before you get on your flight to go to the event. But very nice work, generalizing this, applying this Simon's algorithm to attack a whole host of symmetric functions. Again, you do need to query in superposition. So I don't have time in this talk to really discuss what that means in practice. It certainly means we have a lot of work to do in understanding what it means for a symmetric function, a symmetric cryptography, to be safe against quantum attacks. So Simon's algorithm, I've already stated one generalization in some applications. You can generalize it in many different ways. So when you generalize things, it's great. On the one hand, it's good because it's more general. You can apply it to more things. On the other hand, things can be so general you don't even know what to do with it anymore. But one, I think, reasonable generalization of Simon's problem, and it also generalizes Shor's order-finding algorithm and discrete log algorithm, is known as a hidden subgroup problem. You have a function f that maps some group to some set x with the property that f at x equals f at y if and only if x and y generate the same cosets or in the same coset of some hidden subgroup. So there's a subgroup of G. Right? And you have a function that essentially is constant on all the cosets. And it's constant on the subgroup S. It's constant on any coset of S. But on distinct cosets, it's different. So if G is abelian and finitely generated and represented in some reasonable way, then you can find generators for that hidden subgroup. This is what you can generalize the early known quantum algorithms to. I mean, Simon and Shor's. So some concrete examples. Now, Shor's algorithm is really an order-finding algorithm. G was Z, X was the multiplicative group of integers modulo n, where n is the number you wanted to factor. And F took an integer x and mapped it to a to the x mod n. F is periodic, with period equal to the order of A. Suppose the order of A is R. So a to the R is 1 mod n. So a to the x is equal to a to the y if and only if r divides x minus y. Right? So in other words, x plus rz is equal to y plus rz. Rz is just the integers, all the integer multiples of r. And again, the algorithm works just as well. You can pick your favorite periodic function. So a to the x mod n happens at period r. Pick any function with period r. It'll find that period r for you. Okay. And again, Peter realized you can use this to factor by a well-known method. It's ultimately a difference of squares method for factoring. Discrete logs. When Peter figured out you could break RSA with a quantum computer, people, ever since the beginning of public key cryptography, went to bed at night worrying that somebody might come up with a better way to factor. But we could rest assured, because even if they learn how to factor better, we at least have discrete logs. We at least have elliptic curves. Right? There's a backup. There's a failover. Except Peter broke all of them in the same paper. By the way, in addition to factoring in polytime, I can solve discrete logs. Of course, he talked about finite fields. But you look at it and you say, yeah, and it also applies to the additive group of points on an elliptic curve over a finite field. Right? And there's a group G in this case. The group is ordered pairs of integers mod r. So we assume we know the order of A because we have the order finding algorithm. So you want to find the logarithm of b to the base a. So b is a to the k for some integer k. What's k? And if you let f at x equal a to the x times b to the y, it's easy to see that a to the kt times b to the minus t will equal 1, right? So that's your hidden subgroup. So if you find the hidden subgroup, you've found the algorithm. And the way the algorithm works, it samples things orthogonal to that 2-tuple, to that pair. And then it's really easy to find k when you do that. But you can massage this to look like a hidden subgroup problem. Now Grigoriev, very early on, he wrote this paper on shift equivalences of polynomials over finite fields. A not very well-known paper in our community. So let G be n tuples, Galois field of order Q, n tuples of field elements. Let X be polynomials in n variables over that field. And let F map n tuples of these field elements to polynomials over that field. Right? And the way you do it is there's some fixed polynomial P, and the n tuple A goes to that polynomial with its inputs shifted by A. So P at x1, x2, x3 up to xn goes to P at x1 minus a1. Right? So if P at x1, x2 is equal to x1 squared plus x2, then 3 comma 2 goes to x1 minus 3 squared plus x2 minus 2. Right? And the question is, sometimes you might get back the input. Not in this case, but sometimes you do the substitution, you get back the initial polynomial. So it shifts to itself. These are self-shift equivalences. Right? And the kernel of that map is a subgroup of G, right? And Shor's algorithm will find it. And Dima's paper also studied shift equivalences. I give you 2 different polynomials. Is this one a shift of that one? Right? Or what is the shift that gets you from here to there? It's more of an orbit type question. It's harder, actually. So I don't know of any applications of this in cryptanalysis, but maybe you'll find one. Can this be used to attack multivariate cryptography, for example. I don't know, but it'd be interesting, right? People started looking at Simon as a tool to attack symmetric ciphers, and they came up with all sorts of interesting things. There's another example called the abelian stabilizer problem by Kitaev. I won't define it here. It's very close to the abelian hidden subgroup problem, in fact. One interesting application is decomposing abelian groups. So if you take group theory, you'll know that any finite abelian group is a direct sum of finite cyclic groups. It's an existence proof, though. Okay? So for example, Zn star, the multiplicative group of integers modulo n could be, for example, the product of two large primes. That's abelian. Therefore, it's a product of a bunch of cyclic groups. Right? If I have this decomposition, I can factor n. So, although it exists, it's not so easy to find this decomposition. And the hidden subgroup problem finds a decomposition very easily. Who cares? Well, it's had some interesting applications lately. I mean, Watchers told me that, pointed out to me, to us, that you can compute the class group and class number of a quadratic number field, not an arbitrary number field, just a quadratic number field. The more general case is hard, and I'll get to that in a few minutes. Recently, it's been used, for example, to compute the zeta function of a genus G curve, and especially relevant here, Childs, Zhao, and Sukharev used it to construct their elliptic curve isogenies in sub-exponential time. This is one of the tools they use in this paper. They used a number of interesting methods. So this has already had several applications, this very simple primitive of being able to decompose an abelian group into its cyclic subgroups. What about non-abelian hidden subgroups? You can take the same, when I defined it, I didn't actually say abelian. All the examples I gave, if you happen to be abelian. So imagine the symmetric group. So the group of permutations of n elements. Let them act on a graph. Let G be an n-vertex graph. So let X, the output space, be permutations of the graph. So there's a natural action of a permutation group on a graph. You permute the vertex labels by the permutation. Let F map the symmetric group to the set of graphs by mapping, again, the permutation to the graph permuted by that permutation. You'll notice that F at pi 1 equals F at pi 2 if and only if there's some subgroup K, pi 1 K equals pi 2 K, and that K is actually the automorphism group of G. So it's a set of permutations that fixes G. And until recently, we thought this might be a hard problem. Of course, Babai's recent work says, graph isomorphism and the related problems have quasi-polynomial time solutions. But the hidden subgroup of Fg is the automorphism group of G, and quantum algorithms, the natural approaches for applying quantum algorithms to this have failed. Okay? Although it turns out there's a classical algorithm that's quasi-polynomial. But it doesn't seem, just because it turns out that graph isomorphism, automorphism is not so hard, the rest of the non-abelian hidden subgroup problems haven't toppled. So an interesting case is the dihedral hidden subgroup. Right? So dihedral group, Dn is pairs of a bit, so 0 or 1, and an integer mod n. So it's a pair of numbers, b and x. B is either 0 or 1, x is a number from 0 to n minus 1. So there's the hidden subgroup. We focus on the groups of size 2. There's groups of size n as well. But focus on, this is interesting for subgroups of size 2. So there's one element, one non-trivial element of order 2, and the identity, of course. It's an additive group. The identity is 0, 0. So f at bx is equal to f at b prime x prime if and only if they're either the same, the inputs are the same, or they differ by this fixed pair, 1 comma s. Now, I'll tell you a little bit. Normally, I'm not telling you too much about how these algorithms work, but let me tell you a little bit about how they work. This one works. So a quantum computer can easily compute so-called coset states for a random coset. So random x, it prepares a superposition of the inputs that map to the same output. In 0 comma x and 1 x plus s mod n have the same output. So you can easily prepare a superposition of the pre-images of a random element. And you kind of feel like, oh, I'm holding the answer in my hands. Surely I can extract s. It's actually pretty hard. There's no magic way to do it. Because if you repeat, you're going to get a different random x. So it's not like, if you get the same x, then it's easy. You just keep sampling. Eventually, you're going to get 0x, and some other time you get 1x plus s, and you subtract and get s. But you're not going to get the same x. It's exponentially unlikely. However, if you Fourier transform this and measure, you're going to get a random integer k and a qubit where the relative phase is s over n. I mean, you want s. So if you could estimate s over n, you're in business. You're done. Except I'm going to scramble it by a known k. And you can repeat, but you get another k, a completely different random k. It's really annoying. If I could get k equals 1, k equals 2, k equals 4, k equals 8, some super increasing sequence like this, then it's easy. The quantum Fourier transformer, basic, really simple phase estimation, will extract s for you. Except what are the chances you're going to get k equals 1, 2, 4, negligible. But Kuperberg came up with a sieving method. He samples 2 to the exponential and square root n of these qubits. So there's random k's. And there's a simple method for taking one qubit that encodes k1, another qubit that encodes k2, so k1s, k2s, and produces at random either the difference, k1 minus k2, or the sum. So with 50% probability, you cancel out the bits. So you want to erase all the bits except, get a low order 1 or a 1 in the second bit position or the third bit position. So he had a method for canceling out square root n of those bits at a time. Right. So starting off with sub-exponentially many samples, he can create this qubit or this qubit or this qubit. And he creates them all, and you can determine s that way. So it's sub-exponential. This is a useful quantum algorithmic tool. And Regev showed you can also construct these states if you could solve average case subset sum or learning with errors. He also showed that if you could solve the dihedral hidden subgroup, then you could solve unique SVP with a certain parameter. Many of you have probably seen these results. This is a fundamental part of lattice-based crypto. What's another application of the dihedral hidden subgroup algorithm? So here's another way. Here's a way, we thought we might be able to salvage Diffie-Hellman because it's such a nice protocol for ephemeral key establishment. It's just so nice. So instead of sending G to the A and G to the B, and what if I let the group act on something? It's a nice way to obfuscate the group structure in a sense. Because if I have 2 permutations, say, I can easily compose them. But if I have a permutation acting on something like a graph, so if I have a permuted version, pi1 acting on a graph, pi2 acting on the same graph, and I give you the 2 graphs, good luck trying to find pi1 composed with pi2 acting on the graph. That's hard. But you can still do key establishment. So instead of sending G to the A, you send G to the A acting on X. Bob sends g to the b acting on x. Since Alice knows a, she can compute g to the ab. Bob knows b, he can compute g to the ba. It's the same. And you get a key. And it's not clear how to apply Shor's algorithm to this. If you obfuscate the group structure, you can't actually apply Shor's algorithm. I spent a lot of time trying to build quantum money out of that idea. It's hard. But Childs and Ivanyos, if you read their recent paper, they point out that you can use sieving to break this kind of key establishment in sub-exponential time. So it's not a showstopper per se, but we'd really like something without a sub-exponential attack, if possible. They also, again, I don't have to, like I said, this is not going to be a comprehensive lecture, but it's a nice paper. Rainer Steinwand asked, what about working in semi-groups instead of groups? And they showed you can actually solve discrete logs in semi-groups. So the non-abelian HSP, there's a lot of tools for attacking special cases of it. I mentioned sieving already. Pretty good measurements. You can manually sort of reduce them to abelian cases and so on. A non-abelian Fourier transform. You can also generalize the abelian HSP in a different way. So one way is to go to non-abelian. Another way is to observe. So first, there's hidden shifts, hidden translations. I'll give you some references for this stuff. Gauss sums. This is nice because there's no black box. But one way to analyze it is to generalize it is to note that the hidden subgroup problem can be thought of as a hidden sublattice problem over the lattice of integers and tuples of integers. It's the same thing, just different language. So then wait a minute, what about hiding a sublattice of n tuples of real numbers? Now it's a hassle when you deal with real numbers because how do you specify them? It's all the precision issues, but that's life. There's ways of dealing with it. Okay. So there's some hard technical work to be done, but it's a well-defined paradigm, well-defined problem. If you can solve these problems, you can solve things like Pell's equations and the principal ideal problem and so on. So Feng Song lent me his soda talk slides from a few weeks ago. So some lovely pictures of the continuous hidden subgroup problem on R to the M. So there's a really wonderful paper by Eisentrager, Hallgren, Kitaev, and Song. I think a nice breakthrough paper in the field where they found efficient quantum algorithms for this continuous version of HSP. It's continuous because f at x isn't a string, it's some quantum state, right? There's some continuity there. And they found an algorithm for solving it, okay? Who cares? Well, with that algorithm, they could find the unit group in arbitrary degree number fields. Previous to that, Sean Hallgren and Schmidt and Fulmer did it for constant degree number fields, but they did it for arbitrary degree. And the principal ideal problem and class group problem, again, it had been done before for constant degree number fields. This solved it for arbitrary degree. And there's references to a lot of all the background work in their SOTA paper. Right, so it solves a number of problems, including breaking a couple crypto systems. So let me switch gears now. So I've talked about all these algorithms that offer superpolynomial improvements, superpolynomial speedups over the best known classical algorithms. And again, in a black box or query model, you can prove they're superpolynomial or exponential speedups. But in non-black box, for non-black box problems, of course, you can't prove a superpolynomial speedup, exponential speedups, without separating P from NP or something like that. So the superpolynomial speedup algorithms Great speed up, very niche in terms of what you can apply them to. Searching, on the other hand, the speed up's only quadratic, but it's applicable to just about anything. So here's the searching problem. You have a function that maps n-bit strings to 0 or 1. You have a way of computing it. Find an x such that f at x is 1. So in other words, there's a property. You know how to recognize the answer, so find me an answer. So this is just a generic, generic NP problem. So pick your favorite NP complete problem, 3-set. It's an and of a bunch of clauses. If you give me an assignment, I can easily check if it satisfies the 3-set formula. So it's easy to compute f at x. Good luck trying to find x that satisfies f at x equals 1. That's NP complete. Okay. You can certainly factor, you can solve, you can break any of these crypto systems if you could do this efficiently. Now, suppose there's t solutions to f at x is 1. So classically, if you just randomly sampled, you have a probability t over 2 to the n of getting an answer. So you repeat that roughly 2 to the n over t times, and you're almost certainly going to get an answer. You get this famous square root speed up using Grover's algorithm. It was analyzed nicely by Boyer, Broussard, Hoyer, and Tapp, right, and generalized to many solutions, and they give the exact stop times and so on. So you get the square root speed up. And not only is it a query speed up, all the other non-query operations are also very, very efficient. So it's a real practical, useful algorithm in a sense. And you don't even have to know how many solutions there are. A really important point for quantum cryptanalysis is how well does this thing parallelize? So Zelka showed, so one obvious thing to do, if you have m quantum computers, you can just split up the search space into m chunks and do separate searches, right? You can't do any better than that, it turns out. It's too bad, but that's life. So, in other words, you take the search space, you divide it up into m chunks, and you run them on separate processors. You get your square root speed up on each processor. So why am I making a point of this? So suppose you want to attack AES 128. And let's just count the number of function evaluations to keep it simple. So classically, if you have one processor, you have to do about 2 to the 128 guesses, roughly, before you find the answer. Of course, you're probably going to run this in parallel, right? So let's just say you're doing 2 to the 40. So when you say 2 to the 128 bits of security to invert this encryption function, you know you can parallelize, right? You can do one processor going for 2 to the 128 time. You can have 2 to the 128 processors. Not really, but in theory you could, going for 1 unit in time. But you might have, say, 2 to the 40 going 2 to the 88 units in time. Quantumly, you get the square root speed up, so 2 to the 128 depth goes to 2 to the 64 depth. When you parallelize, say, on 2 to the 40 processors, the running time becomes 2 to the 44. Okay, because it's 2 to the 128. You divide it up into 2 to the 40 chunks, so you get 2 to the 88 per chunk, and you get a square root speed up on the 2 to the 88, so you get 2 to the 44. So what you don't shave off 40 bits. Like here, if you throw 2 to the 40 processors, you divide time by, you take off 40 bits off the time parameter. But with quantum parallelism, you just take off half of that. Okay? So this is how you count. So it's a slightly different meaning to 64. If you want to call this 64 bits of security, you have to interpret that slightly differently when it comes to throwing parallelism at it. Now, Grover, it's a very broadly applicable thing. You can look at your best available, or even not your best. You can look at your second, third best available algorithms to attack conventional cryptography and see how it speeds it up. And sometimes when you apply Grover to something, you apply quantum searching to something, the slower algorithm becomes the faster one, because it's more amenable to a quantum speed up. So sometimes you take your algorithm, you make it less efficient, so you can actually speed it up with a quantum computer. Okay. And we did this analysis for finding short vectors in a lattice, for example. And the constants and the exponents went down a bit. And they guide your parameter choices when you're doing lattice-based cryptography. That algorithm we described here, as well as Kuperberg's algorithm. In Kuperberg's algorithm, he needs a ton of memory. The way his initial algorithm, it needed a ton of qubits. Ours uses a ton of bits. But we point out in our paper, actually, most of the memory, it's just classical bits. You need to query it quantumly, but it's actually just a classical bit. They're not superpositions. So it's what Kuperberg called, quantumly accessible classical bits. And there's super polynomially many of them, sub-exponential or exponentially many of them. But they're only classical bits that have to be queried quantumly. And there's only polynomial and then real computational bits where you're actually going to do quantum algorithms on it, other than looking it up. So surely this is more like having a poly-sized quantum computer than a sub-exponential or exponential-sized quantum computer. Right? Or maybe not. We don't know. There's this really clever idea for a quantum RAM, which seems to work if under the right assumption, under the stated assumptions, it works if you're making a constant or a small number of queries. But if you're making super polynomially many queries, then what? So is the cost of many quantumly accessible classical bits comparable to the cost of maintaining that many computational qubits? If it is, well then these are not so practical algorithms in the short term. It's just not clear. It's an open question. And that'll guide how realistic some of these quantum attacks on post-quantum cryptography are. Now, quantum searching can be generalized. It applies not just to randomly sampling, uniformly, randomly guess, uniformly at random. Because often you can do better than that classically. And Boyer, Broussard, Hoyer, and Tapp showed you can quantumly speed up any heuristic. So you have some algorithm that guesses a solution with probability p. So classically, you have to repeat 1 over p times, right? But quantumly, you can do square root of that much work. So you get the full quadratic speed up for any heuristic that succeeds with probability p. And it uses, square root 1 over p applications of your guessing algorithm and of your verification algorithm. So UF is the subroutine that checks if f at x is 1. So one way of analyzing it is the following. Let S be the sampling cost, C be the checking cost, and P is the probability that you have a solution. That each guess, each sample is a solution. The running time of naive classical search, well, you have to do 1 over P guesses followed by a check. You guess, you check, you guess, you check. You repeat that roughly 1 over P times. So your running time is 1 over P S plus C. Quantumly, you put a square root in front of the 1 over p part. So this is useful when S and C are cheap. It's easy to sample, it's easy to check, but you repeat many, many times, you get a big speed up. So you can see how this is broadly applicable to just about any heuristic. Any simple heuristic, just guessing heuristics. You can apply it to more complicated problems where sampling and checking maybe isn't so cheap. So say you want to solve element distinctness. So you have a function from n bits to some set x. You want to find two inputs that give the same output, two distinct inputs that give the same output. Now, the worst case instances are where it's a one-to-one function except in one case. So there's only two things that have the same output. Everything else is distinct. So it's almost a one-to-one function. That's really hard. Classically, you pretty much have to sample the whole space to find that one needle in a haystack. So quantumly, what could you do? Let your guessing algorithm guess square root of n random elements. So guess this, square root the whole space. And store those f at xj values in some table. Right? And for every element in that list, check whether, because there's one element, so the worst case is there's just one collision, so to speak. If you could find that collision, you just check to see if it's the collision, if it's the one that has a second preimage in the whole space. So checking the whole space takes square root n time. Right? And since you have your square root n elements in a database, you could sort it. You can check. If you have a good data structure under reasonable assumptions, you can sort it in polylog time. You can check. You can search for whether any one of these square root n elements happen to be that one element that appears twice in the list. So checking takes O tilde of square root n time. So in quantumly, what's the running time? So there's the cost S for sampling is square root n because you got to sample square root n things, so it's on the order of square root n with some polylog overhead. C is O tilde square root n as well, and 1 over square root p. P is 1 over square root n, so square root p is 1 over 4th root of n. So you get square root n times 4th root n, you get n to the 3/4 plus some polylog factors. So that's better than classical, which is O of n. This is the best we know how to do with conventional, naive, Grover, amplitude amplification type methods. No one could come up with anything better. And we were trying to prove lower bounds, and we could never do better than n to the 2/3. So either we're really bad at lower bounds, not really bad, it's not bad, 2/3, 3/4, but that's still a non-trivial gap, or we just weren't finding good enough algorithms. But the conventional paradigm wasn't working for us. So to resolve that open problem for element distinctness, one of my colleagues under Symbinus resorted to this new algorithmic paradigm that was being studied, which up until then was like another one of these things where it's like, yeah, that's interesting, not clear if it'll ever be useful for anything. People were studying abstract quantum walks and the speed ups you get, but it wasn't clear. They weren't really applying them to what I would consider to be real computational problems. But they were developing the foundations for a whole new algorithmic paradigm. And then Ambinus's work was another breakthrough in the field of quantum algorithms. So you're probably familiar with the notion of classical random walks or Markov chain type algorithms. With a quantum computer, you can get quadratic speedups for mixing times, even exponential speedups for hitting times. There's a so-called glue trees problem. If you can find a useful application of the glue trees algorithm, that would be brilliant. Again, it was another very artificial problem designed to give an exponential speedup. Not clear that it's good for anything. If you can find an application, that would be great. But quadratic speedup's still pretty good. And it sped up all these interesting things. Often borrowing, the and/or trees, we tried hard in the late 90s, early 2000s, and then some physicists borrowed ideas from particle physics and quantum walk methods to come up with an algorithm that was better than anything we'd come up with in the more conventional paradigm. So how does this paradigm work anyway? So in addition to the Grover type and amplitude amplification type methods, so imagine classically now, there's some you want to search by walk, right? So you start with some initial state, and that might take you some time to find an initial state. Right? So there's some setup cost, right? Because sometimes you want to determine properties of three colorings of a graph. So you want to walk over all the three colorings of a graph. You have to find your first three coloring of a graph and then start walking, right? So there's a setup cost sometimes with these Markov chain methods. And then you have to check whether you have what you're looking for. And if that doesn't work, well, you take another step. And it might take you time to get from one thing to another thing of the same structure. So that's the update cost. This is how Markov chain algorithms can be modeled. Now, there's some probability that a sample is a solution. Let's call that epsilon. And then there's a spectral gap of the random walk, the transition matrix. Call that delta. So classically, if you search in this method where you do all this work S to get your first sample, then you check it. If it's not an answer, you update, check that. If it's not an answer, update again, sample something else. But you don't sample from scratch. You just take a step from where you are. Then the running time is S plus 1 over epsilon times 1 over delta U plus C. This is just classical. Quantumly, you can put square roots in front of the epsilon and delta. Okay. So who cares, right? What are the applications of this? Well, element distinctness. Here's a quantum algorithm for element distinctness based on quantum walks that achieves that lower bound that we were struggling to match before. So let this setup be sample 2 to the n to the 2/3 elements, f at x. And then you check whether there's non-distinct elements within those 2 to the n third element, n to the 2/3 elements. And if there isn't, we'll take one out and replace it with another f at x. And then check. If you still don't have a collision in that set, take one out, replace it, and keep going. Your chance of getting those two special elements in this set here is 1 over n to the 2/3. You can calculate the spectral gap to be 1 over n to the 2/3. So if you plug it into that formula I gave you, the running time is omega tilde n to the 2/3. So query complexity, it's n to the 2/3. And with reasonable data structures and so on, you can get omega tilde n to the 2/3 total cost. Very often, we can solve it in polynomial query complexity, except the overall complexity is that could be exponential sometimes. So here I'm lumping the two in and telling you can actually do both. The total real cost with reasonable data structures is n to the 2/3. Right, so this was a big breakthrough in quantum algorithmics about a decade ago. You'll see why this may or may not be relevant to post-quantum crypto. Element distinctness and collision finding are very related. By collision finding, say you have a 2-to-1 function. So in element distinctness, it's almost a 1-to-1 function. You have to find that one needle in a haystack. Collision finding, it's 2-to-1, say, or many to 1. But let's just say 2-to-1. The way you can do collision finding by quantum walk is just sample n to the 1/3 elements. Again, there's many collisions in collision finding because it's a many to 1 function. Check is the same thing. Look for collision in the current sample. If you don't find one, remove one element, replace it with another, check again, and just keep walking. So you're walking over huge sets of elements. There's a lot of memory being used in these algorithms. And your epsilon is 1 over n to the 1/3. Delta is 1 over n to the 1/3. So your running time is O tilde n to the 1/3 for collision finding by a quantum walk. Right? And you can't do it with that many queries classically. Okay? Classically, there's a birthday paradox. You need n to the 1/2 collisions. So in terms of queries, you get a significant speed up. Any questions? Okay. But what I'm hinting at is, using a ton of memory, right? This is a point Dan Bernstein made a few years ago. Using a ton of memory, you have to compare it to a classical algorithm that's using that much memory, but actual processors, right? So if you have n to the 1/3, for example, classical processors trying to do collision finding, there's good tested heuristics. They're heuristics, but they work with depth n to the 1/6. So it's better than n to the 1/3. Okay. So it was a heuristic developed by Van Oorschot and Wiener. So this is sketched in a paper and talk by Dan. Stacy Jeffrey did her master's thesis on this. It's still an open question whether there's better parallel quantum collision finding algorithms. So you can do n to the 1/3 quantum queries at the same time. Can you do better than n to the 1/6? Now, one thing I think we can do is we could maybe come up with rigorous algorithms for whatever that's worth. But if you have a heuristic that works classically, you're not going to realistically implement a quantum version just so you can have that warm, fuzzy feeling of knowing it's a rigorous algorithm. This is an interesting open question, which should have important implications for post-quantum crypto. And there's other algorithms and algorithmic paradigms. Okay. So Hamiltonian, actually, when Feynman came up with the idea of quantum computing in the early mid-'80s, his idea was simply that it's really hard for a classical computer to simulate 100 or n simple quantum two-state systems, say. So if you build a quantum computer out of quantum two-state systems or quantum bits, Schumacher invented the term qubit later, you have a device that seems faster than the best known, than what classical computers can do. So this is a very, this offers for some problems an exponential speed up. Right? So if you have some Hamiltonian, some energy function, e to the iht is a time evolution, according to that Hamiltonian. You can make it time dependent if you want, but so you have some initial states that you can prepare. You can simulate the evolution with high precision on that state, and you can measure properties of it. Quantum computers are really good at doing that. It's not clear you can use this for cryptanalysis, okay? But you never know. One application of this, which maybe is more likely to, you can maybe think of applications, under the right conditions, combine it with eigenvalue estimation. So Kitaev developed this eigenvalue estimation approach to factoring in the abelian stabilizer problem. Combining that method or improvements of that method together with Hamiltonian simulation allows you to solve some very special kind of sparse linear equations. You don't necessarily get the answer, but you can compute properties of the answer. And it's exponentially better. So if all the conditions are just right, you can cook up examples where it's exponentially better than the best known classical alternative. This is another thing to look for when you're trying to, this is another really potentially valuable quantum tool. And more. So there's adiabatic algorithms, which were invented by our colleagues at MIT. It's a really simple paradigm. I mean, there are certain Hamiltonians, there are certain energy functions where finding the ground state is NP hard. Okay? So you have some Hamiltonian H1, finding its ground state is NP hard. Now there's a theorem in physics that says if you start with some Hamiltonian H naught, some system with some energy function, and you start it in its ground state, if you evolve the Hamiltonian slowly enough, so some h at t, or h at 0, say 0, and h at time t is h1, if you evolve it slowly enough, it always stays with high probability in the ground state. So that suggests an algorithmic paradigm of the following form. Start your system off simulating an easy Hamiltonian. You find its ground state, you put it there. You start simulating the Hamiltonian. You slowly change it to the NP-hard Hamiltonian. And then your state will be the solution to this NP-hard problem. The question is, how slow is slow enough? Okay. And we're able to show that you can get your quadratic speed up for searching with this paradigm. So it's not a useless paradigm. And a slight generalization of this, right? Adiabatic computation versus optimization is actually polytime equivalent to general purpose quantum computing. So it's a meaningful paradigm. I'm not aware of any home runs in this paradigm, but it's out there. Topological algorithms. So in the mid to late 90s, Friedman proposed a topological quantum field computer might be able to solve sharp P problems. Okay. Turned out not to work because of precision problems, but it was a really profound, interesting idea. And later on, it was showed that, in fact, regular quantum computing can efficiently simulate a topological quantum field computer based on topological quantum field theory, which was a relief for those of us who did not want to learn topological quantum field theory. But it's a new paradigm for solving problems. Right? And there's certain topological problems, knot theory problems, approximating points of the Tut polynomial or Jones polynomial, which are known to be computationally hard, and special instances of these polynomials are computing things like the number of forests, or a graph or so on, subforests, or number of spanning trees. Interesting questions. And quantum computers can speed up the computation or approximation of some of these points. Is it good for cryptanalysis? No idea. But it's another hammer, another quantum tool. Span programs are another approach to studying the query complexity of certain problems. Okay. There's more. Again, this is not a comprehensive lecture. So, there's Andrew Childs and Wim van Dam wrote a very nice survey explaining most of the things I've already told you, plus other things, more explanation of the non-abelian hidden subgroup problem. And this is more about algebraic problems, which are, probably more likely to be relevant. If you're looking for super polynomial speedups, highly recommend reading this paper if you haven't already. It's already kind of old, but at least you'll get up to 2008. I wrote a survey, and with a student another survey, summarizing a broad range of algorithmic primitives and tools. It's a combination of paradigms and actual algorithms. The last one is 2010. So they're all out of date. But our friend Stephen Jordan at NIST has been maintaining the zoo of quantum algorithms. So that's where you can get, the best known sort of summary of all the latest and greatest advances in quantum algorithmics. So, the state of quantum algorithmics is far, far beyond just having Grover and Shor, okay? It was always beyond that because we had Hamiltonian simulation even before Grover and Shor. And it's just, there's a huge, rich field of quantum algorithms now. So, we have a very, very difficult and important task on our hands, that of understanding which post-quantum systems are actually secure against quantum attacks. Because we have a good decade or more of work to deploy one of these systems. And we'd like to know that what we're deploying is not going to be broken by a quantum computer when we have them. And it's a really hard challenge because we don't have quantum computers. You don't want to have them. You want to deploy them before we have them, but we have to make them resilient to a device we don't have yet, so it's really hard. So we have to do this work. There's a huge array of quantum algorithmic primitives. And there's a huge, deep knowledge and literature in conventional cryptography and conventional cryptanalysis. These are two very deep, difficult bodies of knowledge. So this is a problem which really strongly lends itself to collaboration across the various communities working in these areas. Of course, some people have the time, energy, and they're bright enough to learn both fields and plow ahead on their own, but there's a lot of great collaborations going on, many of which we're going to see at this conference that's starting tomorrow. Some nice papers where you see people from the conventional cryptography community collaborating with quantum experts and doing some very nice work. So I'm delighted to see that this post-quantum crypto conference has been growing from a fledgling conference with a few dozen participants to over 100 a year and a half ago to over 200 this year. That's just a brilliant sign to see so many bright, energetic, young and maybe not so young people interested in learning more about this field, because there's really a lot of hard work that really needs to get done. And there's a lot to be gained by collaboration. And there's a lot of resources out there and a lot more resources that need to be developed. So we have, of course, at Waterloo, we have a training program in quantum safe cryptography, we call it. If any of you are interested in participating in some of our events, some of them are one-off events. Of course, you can also come as a postdoc or student. So many thanks for your attention. Don't hesitate to contact me if you have any questions or any follow-up questions. Thanks a lot for your attention.
Finding short perspective problems, your explanation is too fast.
Yeah, okay.
Sorry.
Well, I didn't really say very much. There's several very clever classical algorithms. Most of them are heuristic for finding short vectors in a lattice. At a high level, the structure is sample a bunch of vectors, and then you start, sieving, or you do lattice basis reduction to get a nicer set of vectors that are sort of more orthogonal and so on. So it's a very iterative algorithm with a lot of vectors in them. There's subroutines in there which are simply saying search for a vector with this or that easily checkable property. And that's where you can plug in Grover and get a speed up for certain pieces of a very complex algorithm. So it does take a bit of skill or knowledge. That's why I was collaborating with Joop and Thijs. So very bright young people working in many different areas of cryptography. They did the hard part really, which was explain, go through the algorithms, see where there was a very naive search component. In some cases, you kind of have to make it like a less clever algorithm so you can apply Grover to it. And then we just rebalance the whole algorithm. Because when you have a complicated many-step algorithm and you figure out a way to speed up one part, you rebalance all your parameters so you can get your optimal running time. So we did that work and came up with new exponents for a number of heuristics for short vectors and SVP. Okay.
So we always see a quantum algorithm as a tool to break a scheme. So do you are aware of any work which do the opposite, try to use quantum algorithm to improve the efficiency of some crypto systems? So let's say
Yeah.
multivariate crypto, sometimes the decryption could be.
Yeah. So the spirit of post-quantum cryptography is you want something that mere mortals could implement today, but will be secure against these powerful quantum devices of the future. Because we want our systems, first of all, take a long time to transition. So even if you don't have long-term security needs, you still have to do it that way because you're going to deploy something that's going to be in the field for decades sometimes. So you have to be secure against tomorrow's technology using only today's technology. So for most applications, you don't have the luxury of having a quantum computer to build the systems. You have these weak tools. Maybe you could use QKD in some cases, right? And in more and more cases. But that's as far as you realistic in quantum random number generators. These are the kinds of tools which you could argue are practical today and we could use to defend against these quantum computers of the future. But there's an intermediate, so it's a really good question, there's an intermediate phase of that actually some colleagues in Japan, Tatsuaki Okamoto and collaborators, over 15 years ago proposed a scheme where you use a quantum computer to set up the system. So it's expensive, it takes time, but you're just setting up your parameters. And then the execution of the system was purely classical. That's sort of an intermediate, realistic, still can't do it today, but you could imagine that's, you're not going to have a quantum computer to do your encryption and signatures in most cases, but if it's a matter of getting access to this device to set up your system once, it's a little less unreasonable, let's say. And in that paper, they also cooked up a version that didn't need a quantum computer. They kind of rigged it. So they used the quantum computer to compute discrete logarithms to set up a system. And then they came up with, you can find groups where discrete logarithms are easy. So they cooked up some groups where discrete logarithms are easy. Of course, you'd have more confidence in the groups where you needed a quantum computer to find the logarithms. But so there is that one algorithm is the only one I can think of offhand. There's a whole, you can think of quantum public key cryptography and so on, but that's a little more futuristic and not consistent with the spirit of post-quantum crypto, where we want systems that are deployable today and secure against quantum computers of the future. I'm sure you can certainly speed up implementation of arithmetic and so on in some cases with a quantum computer, but it's not in the short term. It's not a luxury we have. And I don't know the status of that Okamoto et al. System. Do you mind bringing him the microphone?
Maybe this is not related to your talk, but personally, we are studying post-quantum. The assumption is quantum computer is available, but we have a lot of controversial if quantum computer is feasible or not. So it's
sorry, I didn't.
Expect that when the quantum computer can be used for design or breaking, it will be difficult, but I like to know your expectations.
So I wrote a paper on the IACR. I've given talks on this, but I wrote up my thoughts and put on the IACR a few weeks ago. Because I came from classical cryptography, and I started working in quantum algorithms because I realized the stuff I was doing would eventually be obsolete anyway. But I've always been following, conventional crypto. And I started getting very nervous about 5 years ago because we know how long it takes to transition from DES to AES, right? To fix these real-world systems, to change them. While you could say quantum computers are decades away, quantum proofing is decades away. So, is this number of decades bigger than this number of decades or less than this number of decades? I was worried about that crossover point. There's, the x plus y is greater than z argument that I've written about. And that's just forget about long-term secrets. Just having reliable post-quantum crypto deployed in all the places you need it before quantum computers are breaking it, even that's getting a bit close, I think. So why do I think it's getting close? In the mid-90s, when I started off in this field, my thesis committee asked me, when are you going to have quantum computers? I tried not to answer the question, but they forced me to. So I said, I think we're going to have 20 qubits in 20 years. So that's this year, later this year. And number of groups around the world are working with, on that, a few tens of qubits. Because we didn't even know what we'd make our qubits out of, let alone be in a position to be scaling them into fault-tolerant systems. But 20 years later, there's some definitely viable alternatives. There's a lot of work to be done. You don't want to underestimate the threat, but you don't want to overestimate it. You're trying to find, realistic assessments. And there's the estimates are all over the spectrum. Maybe 5 years. Oh, don't worry, it's 100 years away. I think those are very extreme. But what's happened in the last 20 years? First of all, we have qubits. We've gone through that 7-step diagram. We're up to stage 4 now. We're trying to do stage 4. There's viable possibilities. IARPA is, for example, funding IBM to try to produce a scalable fault-tolerant qubit. There's other groups around the world trying to do the same thing. If they succeed in the next 5 years, say, then how long do you think it'll take to scale up to a big enough quantum computer? And how big is big enough? Well, the theorists, we're bringing down the cost of big enough. The experimentalists are building this stuff. When's that crossover point? So another breakthrough in the last 20 years is error correction went from a proof of concept. So if you have these completely unrealistic assumptions about your error model and your architectures, then a 1 in a million error rate is sufficient. Okay, that clearly was not going to be practical, but they proved it was possible. And then, that crazy, I didn't say it was crazy, but that, very speculative, visionary idea about topological quantum computing, which is clearly very deep, and some of those brilliant minds in the world were working on it and continue to work on it. One of the spin-offs of that line of inquiry is a family of error-correcting codes known as topological quantum error-correcting codes, surface codes and color codes and so on. These are much more realistic to implement codes on a 2D nearest neighbor lattice with threshold error rates on the order of 1%. So you go from a 1 in a million error rate on an unrealistic architecture with an unrealistic error model to a 1% error rate on a much more realistic architecture with much more realistic error rates. So those are big breakthroughs. So what we needed to do experimentally used to be up here, and we were down here experimentally. And the theorists have brought the physical requirements down here. Experimentalists are here. They're kind of starting to cross over. You have to read the fine print. Because even in the 90s, we had good enough 1-qubit fidelities. We had good enough 2-qubit fidelities. We had good enough measurements, except they were all in completely different systems, at different times. Now they're able to do not just, it's like completely different qubit systems. Now they can generally do a lot of these things in the same kind of qubit systems, just not necessarily at the same time. So like a decade ago in ion traps, they could do 2-qubit gates, but then the ions were too close together to do the 1-qubit gates. But there are still ions in the same kind of traps. But so there's still a lot of work to be done to get all these performance parameters at the same time in the same system in a scalable way. So it's hard, but so it's hard guessing game now. But there's a March meeting coming up. If you look at the schedule, there's several sessions. There's a session on scalable superconducting qubit architectures. There's a session on scalable superconducting qubit gates. There's 4 or 5 sessions on the different aspects of one kind of qubit. Just amazing progress is being done. So if you follow the performance metric, the relevant performance metrics, which is not how many qubits do you have. We're not at stage 5, 6, 7 yet. We're still trying to do stage 4, which is design a scalable fault-tolerant qubit. So it's not a question of size, it's a question of competence, like of achieving some very key operations. If you look at the metrics for that, they're improving very impressively. So that's why. So the predictions I wrote the last few months are a 1 in 7 chance of breaking RSA 2048 by 2026 and a 1 in 2 by 2031. Just plugging in all these moving parts. So probably not by 2026, but maybe. And more likely by early 2030s. And I'm going to revise my numbers, after I hear more about what happened at the March meeting. But I've been going over those abstracts and talking to my friends there. So I think it's a real medium-term threat. It's, people say it's always 20 years away. Well, think about what we're predicting is going to happen 20 years from now. That's changing. Saying we might have 20 qubits, we might start to have a clue in 20 years, is very different from, we'll likely have broken RSA 2048 in 20 years. So I think a lot has been, progress in the last 20 years has been truly impressive if you've been following it closely. It's hard to communicate it because it's very technical. Number of qubits, what number have you factored? That's a really trivial metric but those aren't the right metrics now. So the real metrics are a little less trivial to understand and follow. Great question. Well, thanks again for your attention.